It doesn't change. What's actually
All right. Okay. Hi, everyone. Hello, hello. So, hello. So I want to start. I want to first finish up talking about project 2. So there is one more. So technically, I told you everything you need to know. So one issue that we had not discussed yet is how do you write and read images to the hard drive and from the hard drive. Now, in Python, there is libraries. In C as well, actually, there are libraries to do that. It's not it's not that it's unavailable, but C has this very minimalist philosophy where they try to include as few libraries as possible with a default C installation. So in principle, you can download the C library for handling images. They're none of them are kind of super easy to use, which is why I wrote my own, which I just gave you. And I'm not really requiring you to read through it or to really completely understand it because it's also kind of annoying. But I do want to give you just a few of the things that you need to know in order to understand it. So this is basically about file I/O for binary data. So the basic idea is we want to write an image to a file. And what's an image? Well, in memory, the image is just a block of numbers, right? So as you remember from last time, we can just take this three-dimensional structure and so this is called rasterize. So the image. So rasterize just means kind of read in item by item, the way, for example, we read the image in or wrote the image as just a sequence of numbers where you first write the first pixel, the second pixel, third pixel, fourth pixel. Eventually you move to the second row and so on. So this is just code rasterized sometimes. So a raster is just like a list. So rasterize means make it into a raster, which is basically a list, not in a Python list sense, but just in the normal sense of a list. So the way it worked is it was whatever, 1 to, so I'm just making stuff up, right? But something like this and so on. And then this is the first pixel, the second pixel, and so on. So you could, in principle, so just store the raster as text, right? So literally store it as 1 to 5, comma 1 to 4, comma 200, and so on. You could do it, and then when you're reading it in, whatever, like get rid of the, and then split on the comma, whatever. Right? The downside of doing it this way is that you're storing a whole bunch of extraneous information. So in particular, if I know that all the numbers have at most 3 digits, don't really need to store the commas, right? So also, if I know, as I do, that all the numbers are between 0 and 255, can more efficiently use, right? So storing as binary. I'm not going to, if you don't know how binary works, I'm not going to tell you now, but the basic idea is like this. So this is not currently on the exam. We will get to binary later, at which point it will be on the exam. Right now, I'm just giving you a very simple analogy, right? So suppose I need to store something like this. So just zeros and ones, right? So if I store zeros and ones as text, need to use 1 byte per digit, right? And that's because, well, like 0 is, I happen to know that it must be either 0 or 1, but in principle, you could store whatever, X, W, @ whatever, right? So you need, if you store it as patterns of bits, so patterns of zeros and ones, you need like several zeros and ones in order to encode whether it's a 0 or a 1, because it could in principle also be something like X, @ whatever, right? But if I store only zeros and ones, can store, zeros as low voltage and ones as high voltage. That's what happens. So that's more efficient, right? So because I only ever get like zeros and ones, so I store the sequence of zeros and ones as just like a sequence of like low voltage, high voltage, and so on, right? As opposed to having to store them as digits or characters, where I would need kind of more complex patterns in order to store every digit because there's more options. So that's kind of a metaphor. If you didn't, or an analogy, I guess, if you didn't get it, then that's fine. We'll do it in more technical detail later. But the basic idea is store each number as efficiently as possible. And don't store commas by relying on the fact that each number will have a fixed number of digits. Right? So if you know that every number is 3 digits, then you don't need to store commas. You just store like 3 digits, another 3 digits, another 3 digits, and so on. So that's more efficient. Does that make sense? Questions? So again, like what you need to get is just the vibe right now. We'll do binary kind of later on in more detail. Right now, it's just the claim that instead of storing kind of text that happens to be numbers, I'm just going to store just the numbers. I'm going to say they're all going to be something like 3 digits. So therefore, I don't need to, like, the commas, definitely not the spaces or anything. I'm just going to store it as a sequence of digits. And that's going to be more efficient, is the claim. Right? So to write a block of memory to a file, you can use fwrites. So this would be block. And then, so for example, the size of every element. So I'm in particular using unsigned int 16, something like that. And then I'm going to say number of elements, and I'm going to say FP. So what this does is write the block of memory that consists of num elements. So for example, this is the type. So this is the type that I want. And yes, to a file pointed by FP. So similarly to read, I can use fread. So again, block, the size of the particular element. And again, number of elements and FP. All right. So if my image is stored in a rasterized way as a block, I can read it like this. I can write it like this. And that's what I'm doing in the project2 library. So in order to know how many elements there are in the image, so this is the number of pixels in total times 3, I need to know the size of the image. So that means that I need, so to read write images, so I need what's called the metadata. Basically width, height, possibly the number of channels. I just assume it's always 3. So color depth, what's suggested by Copilot is you can in principle specify whether the color goes from 0 to 55 to 55, or maybe it goes from 0 to 16,000 or whatever. So in principle, there are image formats where it's not 0 to 55, where it can give you kind of more detail in some ways. Yeah.
What do you mean by number of channels? Are those just RGB?
Well, it could be just RGB. So yes, like the channels usually would be RGB. So in principle, you could have other possibilities, right? So just one channel, that's the intensity, right? And then the image would be grayscale. Another possibility, and that's like most images that you would download, it would be like RGB plus alpha, which is like the transparency level. Right, so that would be kind of another item that's stored for every pixel, which is like how transparent is the pixel. And this is useful if you want to have like layers on your pictures, right? So if you want to combine several pictures, you want to specify how transparent or not transparent is each of the layers. And sometimes that's stored, right? For my library, I just used RGB. So I didn't even specify it's 3, it's just assumed that it's 3. So we can look at what that looks like. So if you go here, that's like the library that they made. So basically the way it works is, so I'll go to the H first. So we have our struct that represents the image. So did I say 16 before? I meant 8. So in the image struct, you have the raster. So this is like the block of pixels where each pixel is 3 numbers. So uint8 is just a small integer, just enough to represent 0 to 255. And then we store the height, we store the width. So this is just inside the image. Inside the structure, and that's in memory. And then we have, so this is given to you. You don't have to read it if you don't want to, although it might be a good example. So here we have a create image function. So that takes a pointer to image, and it'll set image to be the newly created image. So that's why it's a pointer to a pointer, because it starts out as a pointer outside of create image. You send the pointer to a pointer so that you can set the pointer outside this function to the newly created image. So we malloc enough space to store the RGB image. So the RGB image, remember, it's the pointer to the raster, and then the width and the height. And then once that's allocated, we store the height and the width, and we allocate the raster. Make sense? Yeah. So it will be compiled with cimage.c. So you don't submit it. It's mandatory that you use it, and we compile with our own version of cimage. So you don't change it at all. You compile it locally, kind of with what we give you, and then we compile it with the same thing on the base code. Yeah.
For the cimage, I've been running into some issues with storage.
Okay.
Where it's telling me that I'm running out. So it's been on and off, but last night especially, ECF wasn't letting me compile it. I don't know.
You're doing something wrong.
Okay.
No, like.
So I don't know.
Well, I mean, it might be like, like sunspots interfering, but no, I feel like it should be, so it shouldn't be the case that you're running out of space. So if, like, one possibility is, like, if you're writing an image where the height and the width are extremely large because you didn't set them correctly, they can't be.
I run it with Valgrind, and it says that every time I use getPixel, it says invalid read of size 1.
I mean,
what is that?
You're doing something wrong. So I like, it can be any number of things. So like the most usual thing would be that the image is not initialized correctly.
Oh.
Yeah.
But you're using in the example you're typing before, unsigned in 16 chars. The C I imagine is char.
No, I think the C is C.
Okay, whatever. But what 8 bits and 1 pixel?
Yeah, I meant 8. Yeah. Yeah, thank you. I mean, that could work as like, I'm not doing the same thing, right? It's just like like if you wanted to store 16 bits per pixel, you could. But yes, I meant 8. Thank you. All right. Other questions? All right. So okay. So that's create image. And then so here there is kind of a thing that I'm not inclined to explain right now, where because I want to make it kind of cross-system compatible, I have to do a little bit of magic there, which we probably will not get into here. But the basic idea is I want to read in the width and the height. And I'm doing that using fread. So I'm reading one number and then I'm reading another number. So similarly with write 2 bytes, I'm giving it, this is actually 2 bytes. So I'm giving it a number and I'm writing it, not going to explain it. So read an image would be like this. So I'm getting a file name. So that's the name of the file where the image is stored. I'm opening it. And then I'm reading in the height using read to bytes, which is a black box. I'm reading in the width, which is, again, like this. And now I get to create the image. Yes.
Output doesn't become the same thing. It's not because the output advances every time you put a lot.
Correct. Yeah, so FP, like that's the case when you're reading, if you remember, if you're reading from a text file as well. So when like you're reading one thing and then the next time you call fread, you're gonna read kind of the next number, the block size that you specify. It doesn't start from the beginning. All right. And then so I read in the height and the width, which are the first and the second thing in the file. And then I just read in the entire raster, which is this many pixel, this many numbers, each one of size 1. And then I close the file. I think there was a question about get pixel last time. So I'm just providing the get pixel function, which you can use. You can also directly write it. So the idea here is you're getting the image struct, which again contains the width, the height, and the raster of all the pixels. And you're getting the coordinates and the color channel that you want. And this is what we had done yesterday with the formula of getting the channel number COL from coordinates y, x in the image. So you can just call get pixel in order to get the answer. You can also just use the formula directly if you like. There is also a set pixel function, which gets the appropriate thing from the raster. So it's convenient that the image struct has the height and the width because you're just giving set pixel IM and then it looks up the width and the height automatically, which it needs to, because in order to retrieve the pixel from location YX, you actually need to know the width. Because you need to skip, like if you want row number Y, you need to skip Y rows in order to get there in the image. So that's this part of the formula. So we have destroy image, which is just freeing the raster. And then once you free the raster, you get to free the image. The order here is important because information about where the raster is stored is in the image struct. So first, if you freed the image and then you did free image raster, that would not work because image raster would not be accessible once you freed the image. So here I'm also providing a function that just prints the values of the image that's called grad. So that's kind of supposed to be the edge image, but you can of course use it for anything. All right. So this so CIMG just inputs and outputs images in the .bin format, which is not the standard format. And that the reason it's not is that it's like as simplified as possible because I wanted to write something in C that's as simple as possible in order to read and write binary images. So we do provide Bill made a thing where you can convert PNG or whatever other images to the ESC190 bin format and back so that you can look at the images that you produce or the images that you read. So if you drag like the PNG there, then you can get the bin out of it. If you drag a bin, then you can get the PNG out of it. This is important because when you produce the output, you want to know what it looks like. And the way to do it is you produce the bin file, you drag it in, and that'll give you the PNG that you can actually display using your computer. All right. So that's like that. I think that is about all that you need to know in order to start project 2, but are there any questions? All right, so start project 2. I think it's kind of good. I mean, like, I think it's good as an end in itself, and it's also kind of good practice for, practicing structs and stuff like that. And I think the output is pretty cool. So yeah. All right. So that's like that. Questions about anything? Yeah.
How do you convert the bin binary files back into PNG files?
So the same website is going to let you do it, right? So you can convert, it works both ways. So it just looks at the file extension, and depending on the extension, it'll either convert bin to PNG or PNG to bin.
How did you create that animated GIF where there were red lines and then
well, I mean, the way the person had done it, this is actually, like, I think it's a student who did it. So like, you just do kind of separate frames. So kind of for each frame, you make the frame, and then you output it to PNG. And then once you output it to PNG, there is like various tools to make a GIF out of a series of PNGs.
oh, so they just ran the scene carvings again and again?
Yeah,
so the
That's right.
project-
That's right. Yeah. So they repeatedly ran it, and then they dumped the output every time, and then they just input it into a tool that makes a GIF.
Oh,
Yeah. So yeah, that wasn't maybe we should make a thing that does it as well. It would be annoying to do it as a web tool, and it would be more annoying for everyone if we made you do it by yourself. One thing I will say is that there are scripts that we do provide for converting bin to PNG and PNG to bin. So if you output a bunch of bins, there is a Python script to convert them to PNG. So that'll make your life a little bit easier. Yeah.
That I would have thought that they go the other way around.
That's an interesting question. So yeah, I guess this is actually just PNG to bin. So bin to PNG, I think I have it. I'll post it as well. Yeah, that's a good one. Yeah. Actually, there might be. Yeah, so this is just PNG to bin. So bin to PNG is really not difficult, but yeah, I'll make it as well. All right, and of course, kind of the source code for Bill's PNG to bin is also available if you go here, but it's in JavaScript. Well, it's somewhere, but it's in JavaScript, not in Python. Actually, it might just be here. Yeah, so yeah, like the JavaScript code is right there. I'm sure if you plug it into ChatGPT, it'll give you the Python code for that. So okay. So that's that. That's the assignment. And then I think if you didn't look at the handout, it probably sounds kind of overwhelming. It is broken up by kind of step by step. So just like the usual thing, just do it step by step. All right. Other questions? Okay. I want to start. I don't think it's the last topic, but it's a big one, and it's like one of the last topics. So we're kind of, it's almost spring. So I want to talk about graphs. So mathematically, one more thing that I forgot to mention. So, and it might be obvious, but usually files are stored as binary. So kind of the bin file is like an example of how like a docx file would also kind of work that way. Right, so most files are stored as binary, more complicated than what I had shown you with the .bin image format. So, okay. So a graph is like usually in math, people just define it as this is like the tuple that consists of vertices and edges. So what is it? Well, it's like in the picture here. So the vertices or nodes are the things that are connected by edges. The edges are the things that connect the vertices and nodes. Like what's a graph? Well, it's a picture like that where a bunch of things are connected. So algebraically, you would say, okay, like the graph is VE, where V is the set of vertices, E is the set of edges, and then V is whatever, like whatever symbols you choose to represent the vertices. The edges are whatever symbols you choose to represent the edges, and then each edge would be a pair of vertices. Okay, so that's what a graph is this thing where you connect those objects called vertices using edges. So graphs can be used to represent all sorts of useful information. So for example, you might have, whatever, like Expedia.com, where they have a set of airports, cities, and then the airports are connected if there is a flight on a given day between those airports, and not connected if not. So after you've represented things that way, you can try to find like the best route between the cities or something, right? Again, kind of you can think about vertices as classes in the timetable, and then the edges would connect classes whose schedule overlap, right? So you have all the classes as vertices, and then you connect the classes whose schedule overlaps. And then you might ask a question kind of using this structure of, okay, like given this graph, can you select a set of classes that they can take during the same semester, right? So the task would be find me a set of vertices that are not connected. So you could, of course, ask the question directly about classes and stuff, but the point is that there are general purpose graph algorithms for example, finding the largest set of vertices that are not connected that are domain independent, right? So you could say, okay, I have this problem with scheduling. Well, what I'll do is I'll map it to the common graph structure. And then I just have pre-made functions, so either literally programmed or like as algorithms in the textbook, that I can apply regardless of the original domain, whether it was about like flights and airports or whether it was about scheduling classes. So more kind of within, designing programming languages, you can think about objects in memory as nodes or vertices, and then the edges would connect nodes that refer to each other. So the idea would be that if there is an object that's not referred to by any other object, that means that it's not accessible, and that means that you can safely remove it from memory, right? So if like there is no pointer to a particular block, that means that there is no way to get to it anyways. So you can, in principle, dispose of it right now, overwrite it, use that memory for something else because it's not accessible anyway. So again, kind of you can think about this directly, but there are algorithms for finding stuff that's not connected to anything. So you can say, I'll think about it as a problem that has to do with graphs, and then I'll use graph algorithms in order to do that. People actually do that, right? So with, for example, Java, there is Python as well, but it's more complicated. There is what's called automatic garbage collection, where if there are objects that are not referred to by any other object, then the Java, for example, just disposes of those objects automatically. So on the previous slide, what we had was what's called an undirected graph. So it was kind of either two vertices are connected or not. You can also have directed graphs where the edges have a point. So like there is an edge here from V1 to V3, but not vice versa. Or you could have like V3 is connected to V4 and also V4 is connected to V3. So depending on the problem, one or the other might make sense. So if you're thinking about the edges as classes whose schedules overlap, then this is not really directed, right? Because either two classes are connected because their schedules overlap or they're not. There's not really direction here. With flights, obviously, if there is a flight from Toronto to Montreal, it's not actually helpful if you want to fly from Quebec City to Montreal and then from Montreal to Toronto, because having a flight from Toronto to Montreal is not the same as the other way. Yes.
So when implementing graphs in C, for example, would edges just be pointers?
Well, there's various ways to do it. So that's one way to do it. We'll get to implementation. Maybe not today, but definitely on Monday. But yes, that is one way to do it. But right now, this is not really kind of language specific, right? Those are just like mathematical objects where we just say, okay, like you can have an edge that's like from V2 to V1 or something. So graphs can be weighted. Each edge can be associated with a weight. That's just a number. So again, thinking back to flights, you might think that, there might or might not be a flight from V1 to V3, and also it has some kind of cost associated with it. And it could be like various things. It could be literally the cost in dollars. It could be CO2 emissions. It could be distance. It could be time, whatever. And those are probably correlated anyways. Yeah. So there's just like some terminology. So I'm going to try not to use too much, but at the same time, you need to have seen it the once. So V1 and V2 are adjacent if there is an edge between V1 and V2. So in math notation, if there exists an edge from V1 to V2 in the set of edges E. A path is a sequence of vertices in which each pair of vertices that are adjacent in the path are actually adjacent in the graph. So in other words, it's a sequence of vertices, so like from V1 to Vn, and it must be the case that if they are next to each other in the path, then there is actually an edge between Vi and Vi plus 1. So they're adjacent in the path because it's set up so that the vertices are like V1, V2, V3, V4. And what we're saying is that it must be the case that between I and I plus 1, there is an edge. The length of the path is the number of edges in it. So this is like a common thing where people say, like, is it the number of edges or is it the number of vertices? Those are not the same. There is like one fewer edges than there are vertices, right? So the length is the number of edges. And that kind of generalizes nicely where if you want like not the length, but the sum of the weights, then which you sometimes want, like if you want the overall cost of the flight, that's like the sum of the costs between the individual pairs of nodes. So you can think of an unweighted graph as just all the weights are 1, in which case you can sum up the weights and that'll give you the length, which you cannot do with the vertices. Doesn't always work. In fact, in project 2, what we're doing is we're summing up numbers that are associated with vertices rather than edges, right? So, but the usual terminology here is like this. A cycle is when you can go in a cycle in a graph. So if you have a path from V1 to Vn, and V1 and Vn are the same, connected. So that's a cycle. So like V1 is connected to V2 and so on, and then Vn is also connected to V1. So you can go around. A graph that doesn't have cycles is acyclic. a DAG, people say, is a graph that's both directed, meaning there are arrows there, and acyclic. So directed acyclic graph. So this graph, for example, is not directed and not acyclic, right? So not directed just because there is no arrow pictures there, and not acyclic because you can, for example, go like V3, V1, V2, back to V3. What about this guy? Is it directed? Not a hard question. Yes, yes, it is. Is it acyclic? I see ambiguous nods, and yeah, yeah. So a fun fact, in Bulgarian, I suppose not in Bulgarian body language, it's like reversed. So this is like yes, and this is like no. Yeah, I knew that, and then like that would be like 10 years ago on the night bus along Bathurst. One guy literally, I'm not making it up, asked me in Bulgarian, "Do you happen to be Bulgarian?" or something like that. I did not know Bulgarian, but I kind of did understand. But I forgot that the body language would not work. So he was for a few seconds under the impression that I am indeed Bulgarian because. Anyway, so sounds made up. I promise you it happened. It was the night bus in Bathurst, but I was not drunk. Anyway, so okay. So not, going back to this, so not acyclic because you can go from V3 to V4 and back. So here you can also actually, so here you cannot go like this because the arrows don't match. But yes, not acyclic because of V3 and V4 where you can go back and forth. So, okay. So a simple path is a path with no repetitions. A simple cycle is a cycle with no repetition. Two vertices are connected if there is a path between them. So they're adjacent. If there is an edge between them, they're connected if there is a path between them. A subset of vertices is a connected component if all the vertices are connected within each other, and the degree of the vertex is the number of edges that are associated with V. That's kind of for non-directed. If it's directed, you can have an in degree and an out degree as well. Okay. So sorry, I was going to show you a connected component. So for example, V3, V2, and V4 are all connected between each other, so they're a connected component. V4, V1, and V2 are also a connected component. This entire graph, in fact, is also connected, like the whole thing is connected, in fact. So on the other hand, over here, this entire graph is not one big connected component because V2 is only connected to V1. In fact, V1 and V2 are, well, depending on whether you want directed or non-directed, you can say connected or not connected. V3 and V4 are a connected component if you're strict about it and say like they must be connected both ways. So, okay. So to your question, 5 minutes left in the lecture and I'm answering, so that's good. So far we were talking about the graph as if it were an abstract mathematical object, kind of independent of how you actually implement it in code, right? So you could think of it as an abstract data type where the graph is just like this abstract object and it has vertices and edges, and you can ask like, are the two vertices connected? Stuff like that. So here's how you can implement it. So there's two major ways. So one is you can store it as a matrix. So you can just say, okay, I'll have the matrix that's going to be n by n, where n is the number of vertices. And then Mij is going to be 1 if there is an edge between Vi, Vj, and it's going to be 0 otherwise. So you can also optionally, just if you have different names for the vertices. So for example, like if each vertex is like an airport, you can have a list of like airport 0 is YYZ and airport 1 is YVR, whatever. Right? And then the edges you can store as an adjacency matrix. You can also say a linked list is a kind of a graph. It just happens to be a graph where every node only has one arrow going out of it. So we'll kind of generalize it. So we'll store it as what's called an adjacency list for every vertex, right? So every vertex is going to be associated with a linked list, where the linked list contains all the other vertices to which the source vertex is connected. So an adjacency matrix might look something like this, right? So here, for example, 0 is connected to 2 and it's connected to 5 and nothing else. And that's why 0, 2 is 1, and then also 0, 5 is 1. Yeah.
So adjacency matrices, they're usually unweighted, or?
I mean, it depends on the graph. So you can definitely store the weight instead of just 1 and 0. Right? And then, so we'll come back to this slide in a second. And then the adjacency list would look kind of like this. So for example, 0 is connected to 2 and 5. So there's going to be a linked list here that stores 2 and 5. And then 7 is connected to 8. And 7 is also connected to 2. So that's why 7 has 2 and 8 as the list of vertices that are adjacent to it. So to your question, actually, yes, like you could have a weighted adjacency matrix where if the edges are associated with a weight, instead of storing 1 and 0, you store, the weights. In this case, what you usually want is you want to say the cost of getting from 2 to 0 directly is just infinity. So there is a problem there because you could in principle have like 0 weight, and 0 doesn't mean not connected necessarily. So you need to have a special symbol, for example, infinity, which would be kind of what does it cost to get from 2 to 0 directly. So infinity works with that. Of course, not necessarily. Depending on the problem, it might not be that intuitive, but you have to have something special to indicate no connection. All right. So with the adjacency list, of course, you can also store weights, right? So you can say 0 is connected to 1 and 3, and the costs are 8 and 6. If it's not directed, then usually you would just store both. You would store both connections. So you would store the connection from 0 to 1, and you would also store the connection from 1 to 0. So it's stored twice. In here as well, if it's not directed, then the matrix is just going to be symmetric, right? Because the connection from 0 to 1 and the connection from 1 to 0 is the same connection with the same weight. If it's directed, then the matrix is not necessarily going to be symmetric. All right. Okay. You got through the week. Congratulations. I think next week should be better. Hopefully, is it? I don't know. So yeah, enjoy the weekend. By the way, yeah, by the way, oh, thank you. Yeah, so I went to school night on Wednesday night because I didn't have an MSc midterm. I recommend it. It's good. So yeah, you should check it out today or tomorrow. Yeah, bye.